All right, here we go. Putting the pieces together, I'm wondering if you were able to correctly guess the fifth degree term. So let's see. So whenever we were forming the fourth degree polynomial approximation for f of x at f of x equaling e to the x at x equals 0, we essentially found the fourth degree term by, did you guess it? Factorials, which tied it nicely all the way back to the very first warm-up. Right, and so let me show you how that plays out. Okay, so I tried to give you try to lead you in that particular direction. So here is our fourth degree polynomial, approximating polynomial. Whenever I take its first derivative, not seeing many factorials there. Okay, so let's take the second derivative. So when I take the second derivative, notice that I have 2 times a totally unnecessary 1, and that 1, of course, is coming from the 1 that is on the x here that we would leapfrog down 2 times 1, and the reason why I wrote it like that, because 2 times 1 is 2 factorial, right? Okay, so let's keep going. I take the third derivative, and on the third derivative, I'm going to have 3 times 2 times 1, because just like before, the 1 that's on the x is going to leapfrog down, and 3 times 2 times 1 is 3 factorial. Okay, one more time, fourth derivative, I'm going to have 4 times 3 times 2 times that understood 1, which is the same thing as the 4 factorial, times a. In this particular case, we're going to set that equal to 1, and then we divide it over, and we get 1 over 4 factorial, which is 1 over 24. Where did that 1 come from again? Well, that 1 came from us taking 0 and sticking it into the fourth derivative, which just happened to be e to the x. It's not always going to be 1. It just totally depends on the function and its derivative, its fourth derivative, whatever. Okay, so let's see then if you, for real, got the fifth degree term right. So the fifth degree derivative, it's going to look like this. The only term that's going to be left is the leading term, that x to the fifth term. Originally, it was a x to the fifth power. So when you keep taking its derivatives, it's going to be 5 times 4 times 3 times 2 times 1 times a, which is the same thing as 5 factorial times a. And for the case in point, the function in question, we would set that equal to 1 and divide over our 5 factorial. 1 divided by 5 factorial is 5 times 24, that's 100 and 120. Right? And the 1, again, just going to write it down again, it comes from 0 plugged into the fifth derivative, which may not always be 1. All right, so now we got to take that coefficient and multiply it times x to the fifth power. And so our fifth degree term, if you guessed it correctly, should have been 1 over 125 times x to the fifth. Okay, so let's see if we can generalize this. Instead of finding the sixth one, let's just go straight to the nth one. So whenever I have an nth degree polynomial and I take n derivatives of it, the only term that's going to be left or is going to contribute to that derivative is the leading term, the one that was a times x to the nth. When I take its derivative, it's going to be, leapfrog that n down, n times n minus 1 times n minus 2 times ... skip a few, times 3 times 2 times 1, all of that times a. All of the numbers in front simplify down to n factorial times a. We're going to set it equal to 1 because that's 0 plugged into the nth derivative. Divide over your n factorial, and there you have your leading coefficient there. And now I just need to multiply that times x to the nth in order to get the actual term. So over here in general, I'm plugging 0 into my nth derivative, divided by n factorial, and multiplying it times x to the nth. Now we're almost there. Here's the thing though. E to the x centered at x equals 0, very, very easy thing to do. But not all functions can you center it at 0. So think of the natural log of x, which is graphed right here in this little logo. So we can't center it at 0 because it's got a vertical asymptote there. It's not even defined there. So usually natural log is in some kind of way centered at 1. So in order to center it someplace else, I think the easiest way to accomplish this is by just doing some SRT transformations, specifically the t part, that we're just going to translate it. We're going to do the same work that we did before and just translate it to the right or to the left by c units. Okay, so its coefficient is going to be identical to the coefficient that we had before, because you're going to leapfrog down that nth power times n minus 1 times n minus 2 and so on. It'll be n factorial times a. But this time you're not going to set it equal to 1. You're going to set it equal to the nth derivative evaluated at c, whatever that c value is supposed to be. Common numbers include like 1. If it's trig, it could be some sort of radian angle measurement like pi over 2. Right? And then to solve that thing, you solve it for a by dividing over the nth factorial. So here is your general coefficient. It is the nth derivative evaluated at your center point, all divided by n factorial. Now we have to multiply that times the term, the x thing, but it's not going to be x to the nth because we've just translated this to the right, c units. What's it going to be? Well, our term then is going to be this coefficient multiply times x minus c raised to the nth power. Again, we've got the nth derivative evaluated at our center point divided by n factorial multiplied times x minus c, our center point again, all raised to the nth power. And this is the general term of what we're calling a Taylor polynomial. Okay, so here then is the formal definition of a Taylor polynomial. An nth Taylor polynomial, if f has n derivatives at c. So of course, like look at the first question that we did. We had to keep taking derivatives. Transcendental functions, you can take their derivatives all day and never get tired of it. If f has n derivatives at c, then the polynomial that follows, boop, is called the nth Taylor polynomial for f at c. It's called the Taylor polynomial because it's named after this handsome guy over here, Brooke Taylor. Could have swore Brooke had an E at the end. Maybe it doesn't. And you can see the year there, 1715. This is a few years after Newton published his work Principia on, physics stuff and calculus. About 30-ish years, I'm going to say. Okay, so our polynomial looks like this. P sub n of x is equal to f of c. So this is our polynomial agreeing with our function at its point of tangency, okay? Plus the first derivative evaluated at c times x minus c. So now we have the slope matching up. Plus the second derivative evaluated at c divided by 2 factorial times x minus c squared. Now it has the same concavity. And then you keep going so that its general term is the nth derivative evaluated at c divided by n factorial times x minus c raised to the nth. Now I know what you're thinking. Why do the factorials only start at 2? Why is it different for the first two terms? The answer is it's not. It's just we don't have to write them down. So for example, let's go back one term. This is the first degree term. So continuing this pattern, it should be divided by 1 factorial, but 1 factorial is just 1. All right, let's go back to the term right before. This is the 0 degree term, so it should be divided by 0 factorial. What the heck is 0 factorial? Let's call up the calculator here. Boop, calculator screen. And let's just put in 0 factorial. And let's let it shout what the answer is. What's it going to be? It's 1. That's right. 0 factorial and 1 factorial, they're both 1. If you're confused on that, let me point you to YouTube and a number file video that discusses it in detail. For us, though, yeah, there you go. 0 factorial is equal to 1. All right, now, the particular kind of Taylor polynomial that we were forming with e to the x centered at 0, it's got a special name. When it's centered at 0, instead of just calling it a Taylor polynomial, we call it a Maclaurin polynomial, named after this Scottish mathematician Colin Maclaurin. So if c is equal to 0, if it's centered at 0, then your Taylor polynomial simplifies down really nicely, and it's called an nth Maclaurin polynomial. So our polynomial is f of 0 plus f prime of 0 times x plus f double prime of 0 divided by 2 factorial times x squared plus, you get the point, right? And so the story on this is that you can see the year here at 1742. Is that when Columbus? No, that was 1492. Anyway, yeah. So he wrote a paper when he was pretty young. I think he was like some sort of math genius child prodigy, but he wrote a paper that referenced Taylor polynomials. He cited his sources. He gave Brooke Taylor full credit, but it was subsequent mathematicians that said, you know what, to honor this guy and his amazing hair, if this is actually his hair, if a Taylor polynomial is centered at 0, we're going to call it a Maclaurin polynomial. All right. The AP test, of course, uses the same exact terminology. So this next question should be a piece of cake then. Example 4. Find the nth Maclaurin polynomial for f of x equaling e to the x. Without having to do all of that work that we did before, here it goes. So just bear in mind, of course, our function f of x equaling e to the x, its nth derivative, no matter what, is e to the x. It's the only function for which that's true. And then the nth, this is supposed to be in parentheses, the nth derivative evaluated at 0, if it's Maclaurin, our c is equal to 0, of course, is equal to 1. The function value is equal to a 1 there. The first derivative, the slope, the concavity, whatever, it's all equal to 1. Now, I know what you're thinking. You're going, well, why didn't we just write that down for all of those other exercises? And I don't have an answer for you, honestly. Yeah, it would have saved quite a bit of time, wouldn't it? Okay, so anyway, let's write down our our nth degree Maclaurin polynomial for e to the x centered at 0. It would be f of 0. Well, f of 0 is 1. No matter what, it's always equal to 1. Plus the first derivative divided by 1 factorial. First derivative evaluated at 0 divided by 1 factorial. Oh, let's keep the pattern going here. Let's make this 1 over 0 factorial. Okay. Times x to the first plus 1 over 2 factorial times x squared plus 1 over 3 factorial x to the third plus, let's skip a few and go all the way to the nth one, which is going to be the nth derivative evaluated, go away, the nth derivative evaluated 0, which is 1, divided by n factorial times x to the nth. And then maybe I come back over here and just clean this up just a little bit, because 1 divided by 0 factorial is still just 1. And then 1 divided by 1 factorial is also just 1. Boop, boop. All right, there you have it, right? Pretty easy, right? So let's go back to the slideshow and summarize this just a little bit, the process that you go through whenever you're finding yourself an nth Taylor or Maclaurin polynomial for f of x. Well, the first thing that you got to do is the first thing that we did, which is take a whole bunch of derivatives. Step number 1, take in derivatives. If they ask you to find the third Taylor polynomial, take 3 derivatives. If they're being excessively cruel and they want the 12th degree Taylor polynomial, guess how many derivatives you have to take? That's right, 12 of them. Now, what do we do with all those derivatives? We're going to take our center point, our c value, and plug it into those derivatives. If it's Maclaurin, of course, it's going to be very simple. Stick in 0. Anything other than that, whatever that c value is, stick it in. Okay, so that becomes part of our coefficients. We still need to divide each one of those terms by the n factorial, and then you multiply it times your generic term. And that generic term is x minus c raised to the nth power, whatever that nth power is. So in general, each one of our terms of our polynomial is going to be formed by the nth derivative evaluated at our center point divided by n factorial, all of that multiplied times x minus c raised to the nth. So in the next couple of videos that follow this, we're just going to look at a couple of different examples, something a little bit different than just e to the x. Maybe it'll be centered at 0, maybe it won't.